Professor Yan and Professor Xiaoming Tao, Professor Zhiyong Fan for the invitation for me to join this great conference and share with you our research, our recent and past research. So, and also want to thank Professor Xiaodong Chen talk about the 5 senses. And in my talk, I'm going to cover primarily 2 kind of senses. One is optoelectronic sense, which is a visual sense or our eye. The other one is related to the olfactory. So here I call that chemical sensor. So we build this type of device. I'll use the 3-dimensional nanostructures. So before I walk into the technical content, I want to thank the support from 2 platforms. So one is the State Key Laboratory on the advanced display and the optoelectronic technology. So this is a major platform is supporting our research in the past years. So the current director is Professor Meng Wang, and previous directors, including Professor Hoi-Sing Kwok and C.W. Tan, who is the father of OLED. So on this platform, we investigate the materials and the devices for optoelectronics, including the display, solar cells, and the photosensors, etc. So the other platform, which was established by myself, so the Center on Smart Sensors and Environmental Technology. So I'm the founding director of this center. Together with me, we have C.Y. Cui and Baoling Huang as associate director of the center. So under this center, so we have ongoing research from the sensor materials, the sensor device innovation and system and applications for the health and the environmental technologies. So today, my talk, the content, as I mentioned before, one is on the optoelectronic side, the other one is a more chemical sensing side, though. Those are the works supported by these 2 platforms. All right, so this is my research group. We have around 20 to 30 students and postdocs together, and I divide them into 2 subgroups. So one is a sensor subgroup, the chemical sensor subgroup. The other one is the optoelectronic subgroup. I'd like to thank the hardworking students for the contribution to this talk, and also want to thank the funding agencies from Hong Kong and also from central government and Shenzhen and municipal governments. All right, so our research group, we have 5 pillars on the research. So today, because of time limit, I'll cover the photodetector and gas sensor side. So as I mentioned, so this is related to type of important senses that Professor Xiaodong Chen mentioned. So I will firstly talk about nanostructured optoelectronic sensors. So over the past close to 12 years, so we always work on the nanostructured materials and use the nanostructured materials to build the optoelectronic devices. So one of the very important reasons is the early stage we found that there's a capability we can acquire from the nanostructured material. We call that the photon management capability. So especially when the material or device dimension or periodicity is comparable to the photon wavelengths that you want to play with, then we can see very strong photon management capability can be demonstrated by the material and structure. So this is a simple optics. You perhaps already learned in your college. Now, materials. So what kind of the materials should we use? So we're talking about the nanostructured materials. So basically, you can categorize the nanomaterial into 0D material quantum dots, 1D material carbon nanotube nanowires, or 2D material, which is very popular these days, right? Now, if you look at it, so which kind of material is suitable for optoelectronics? I can tell you that there are gazillions of the papers talking about different kind of optoelectronic device built with all these materials. But this is just my personal perspective. I think the 1D material has a good potential compared with the 0D and the 2D. So remember, I just mentioned about this photon management capability and strong light matter interaction, right? So that requires a material dimension comparable to the photon wavelengths. But if you think about the 0D material, with diameter of few nanometers, which is much shorter. So let me turn on my laser pointer here, which is much smaller than the visible wavelengths that we play with, right? So individual 0D material is not a very efficient material to interact with the photons. So as also you know that often we assemble many quantum dots together to form a film in order to make a solar cell photodetector, et cetera, right? But then it lost the capability to interact with the photon again. I mean, in the way that I talked about it before, the regularity and the periodic structure, right? So if you think about the 2D materials, right? If one single layer of a graphene or 2D material is very, very thin and it has a very small optical absorption capability, right? Of course, the other two dimension, you can have a large area or large size, but again, so when we talk about something with a dimension comparable to the photon wavelengths, and so it seems like not an ideal material to me. Well, if you look at the nanometer, at least in the radial direction, so we have two dimensions with a geometry or size comparable to the photon wavelengths, and then we can think of generating some resonant modes. For example, this is what we have simulated in the past. We can generate resonant mode inside the nanometer, single nanometer as like a fiber, optical fiber. Of course, it's a very different type of fiber with we call the single mode or multi-mode fibers, right? But indeed, you can efficiently generate or produce the light-matter interaction inside a nanometer, all right? So at the same time, there are also other merits. So I'll summarize the merits of the 1D material. So I call the 3E merits. So the first one is the easy carrier transport control, which means you have a two terminal, okay? So you can put the leads at the two terminals and you can inject the carrier. So this is very easy to control, right? And the individual 0D material is almost impossible to do that. Of course, 2D material, you can do that, right? So efficient light matter interaction already explained. So the third one is the easy 3D integration. So I'll explain to you what is the 3D integration of a 1D material, right? So this is a 3D integration, right? So you put all the material vertically and assemble them together, you got a 3D array. So what about the 2D material? If you stack them up, then you got graphite, right? So this is not very useful, right? And the 3D stacking of the 2D material, research-wise, is still a very challenging topic. So then my main research topic and contribution over here will be the 3D integration of these nanowires. And earlier stage, we also explored the 2D integration of the nanowires. So we explore the photosensing capability, photosensing performance by playing with energy band gap or the band edge modulation. We can get a high performance, but that's not the key point of today's talk. So one of a very unique process we developed in the past years since 2016 was growing the one-dimensional material into this porous template. So this is the aluminum oxide template, porous aluminum oxide template, and we can assemble the 3D nanowire array with a highly controllable nanowire dimension like radius, diameter, and the length, and of course the periodicity. So I have mentioned the importance of the periodicity earlier for photonic device and the optoelectronic device. It's very important, right? And this type of 3D integration, we can achieve very, very high density. So recently we have a paper published on nanoletter and also on Science of Advance. We talk about the 10 nanometer pitch. So that's a very high packing density. So with this method, we fabricate a planar device, planar image sensor. So planar image sensor like this, right? So we have a crossbar kind of a device, and this device can serve as an image sensor. And just recently, we also combined the so-called quantum wires and nanowires together. So this is a double layer structure, all right? So the quantum wire is basically a nanowire with a very, very small diameter, with diameter comparable to the Gauss radius inside this material, so it can demonstrate the quantum confinement. So by using the quantum confinement, we can blue shift the absorption edge to shorter wavelengths, right? Then by putting these two together, we can use a quantum wire layer as a filter in front of the nanowire layer. Then we can achieve this color selective or narrow band photo detection. So we over the past year, we developed a lot of tricks to play with the nanowares materials for photosensing. So the next question, so we want to go higher dimension. So we talk about 1D, 2D, 3D, it's all about the dimension change and elevation, right? So I mentioned the planar device. So planar device, if you look at it microscopically, you have a 3D array, but macroscopically it's a 2D, right? So what if we build a curved or non-planar sensor, image sensor? So some people call that a 3D image sensor. So on the left-hand side is an image acquired from I think it's a big company called Sony. Yes. So they're fabricating this curved image sensor. All right. So not only Sony, but a few other companies also making that. So the point to make this curved image sensor is just because of the few merits or the advantages. So one is the large field of view. So this is the curved sensor can accommodate a much larger field of view compared with the planar sensor. The second one is a correction of the image distortion at the edge of the field of view. So if you take a photo with our cell phone camera, often we see the people, standing at the edge of the photo, always get the face and body distracted, distorted. This is image distortion. So, but if you have a commercial camera, it can do much better job because more complex lens lens will be used to correct this image distortion at the edge. And also the curved image sensor can fit into some unique applications, such as human like robots or visual prosthesis, right? So, but the curved image sensor will be another, very challenging topic because this is completely incompatible with the current CMOS processing. All right, so but if you look at our human eye, so which has a curved image sensor, hemispherical image sensor, right over here, we call the retina. So if you look at the retina, the structure, so there's a light sensing cell, so photoreceptors. The Xiaodong also mentioned about that. And these photoreceptors, so typically there are raw cell and the cone cells. It's a 3D integration of the photoreceptors, so very much similar to the nanowire array I just demonstrated. So inspired by that, so we designed and fabricated this nanowire array-based artificial or bionic retina. So basically the idea is we firstly take a aluminum material, we deform it to hemispherical shape, then anodize the surface to build this porous structure on the surface and use the previous mentioned the chemical vapor deposition method to grow the nanowire inside, and we form this nanowire you can see over here, right? So the dark red color is the nanowire photoreceptors inside the porous template. All right. And following that idea, we in 2020 we put this work to demonstrate the artificial eye over here. So the core component is a nano array retina, and in order to extract electronic signals, so on the front side we adding the ionic liquid to transport the electron, and backside, so we have these liquid metal nerve fibers installed in the artificial eye socket to form the back contact. All right. So below you can see the image. So this is the SEM and TM image. So this is a hemispherical structure with a 5 micron meters long nanowires embedded inside. The whole structure thickness is about 50 microns. So we have a large space over here filled up with ionic liquid to transport the charge. And the nanowires are single crystalline materials. We can also do the imaging of the letters and the symbols. So this camera, this kind of the camera can have as large as 101 degree field of view, which is almost twice of our cell phone camera. So later on, we also developed new generations of this so-called bionic eye with new material. Our bionic eye can see the IR, the human body, the temperature, the electromagnetic wave radiation, right? Then also we're adding the electronic iris and lens. So these two works are still under review. So perhaps in the future, I can report you the details. All right, so since the theme of this conference is about a wearable, right? So I've been thinking about, how wearable it is, the bionic eye. So this is the the sci-fi movie, the Terminator, right? So it has a very scary eye. So this scary eye perhaps can see IR2 or other band of the light. I wouldn't say this is a wearable form. Maybe it's installed or can be replaced as a robot is not a problem. But how about this version? So I also found this very interesting news called the third eye sensor for smartphone addicts. So what does it mean? So you might walk on the street and see people just look down on the cell phone and walk right on the street. It may run into another person or simply a wall, right? Then there's a Korean company developed a wearable third eye put on the head. You can mount on the head, and this eye basically has a camera, and this camera will image whatever in front of you, and also on the cell phone there's a small screen to show whatever the camera is seeing to give you alert if something approaching. So some threat is approaching, right? So, but I don't know how useful it is, but it's just inspiring. All right. So by showing that, I'm hoping that maybe we can think of some interesting idea to design the wearable sensors, right? Okay, so the real wearable optoelectronic sensor built in our lab, I just show with this slide. Let me see, can I use, can I turn on this? All right, here. So this is basically a UV sensor, which can help to monitor the UV exposure of our skin. All right, so this is made of perovskite material, MAPBCl3, which is a wide bandgap material, right? So my postdoc built such a wearable form. Okay, so we have these sensors over here. We have MCU, and we have a Bluetooth unit and connect with the cell phone. So when we shine the UV on it, you can see the UV index, right? So we can also test the outdoor. Let me just fast forward. All right, so natural sunlight UV index. So we calibrate the UV index. So if it's a green, that's good. If it's red, it's bad, right? So with the cell phone connection, we can calculate the daily UV exposure when you're doing, hiking and etc. The working out, right? All right, so I'm going to switch gear to the chemical sensor and the sensor network. So this is related to the olfactory sense or the sense of smell, right? So our initial idea was to build a sensor network for a smart city or smart home to monitor the dangerous gases such as hydrogen in Hong Kong or formaldehyde, the life-threatening gases, and to give us a very good environment to live. So why we use nanostructured sensors? Many years ago, so you can see my first publication on this topic is 2004, right? So we figure out that if we use the nanostructures, it has a very large surface to volume ratio. It can very efficiently interact with the gas molecules in the surrounding. So this gas molecule, they interact with the material and they change the conductivity of the channel. So at that time we built this field effect transistor. And then something is coming. So for example, nitrogen dioxide can reduce the conductance dramatically, right? Something is coming. All right, so that was a nanowires, but later on we figured out maybe nanowires is very difficult to control the shape and size. At that time we didn't figure out how to go in the template, but later on we do that, right? Then we think, why don't we just use the template itself as a three-dimensional architecture to host the sensing material, which also has a very large surface area, right? So this is the same kind of power structure we use to host the nanowires, if you remember. So inside we can coat the metal oxide material, which is very sensitive to the gases, different kind of gases, right? So we can use a different method to coat them. One of the best method is atomic layer deposition. All right, so see the time. So we use the atomic layer deposition to deposit sensing material inside, and we made a sensor array. So sensor array is very important in order to generate enough data for the artificial intelligence to work on the gas classification later. And the low power circuit board, which also has an MCU, Bluetooth, etc., can acquire the signal and pass a signal to cell phone for data processing. All right. So if you look at the individual sensor performance, the sensitivity is pretty high. It can reach a single ppb level. For example, toluene can reach 1 ppb level. Acetone can also. And for formaldehyde, 2 ppb is also good enough. Just for your information, if indoor we have 80 ppb formaldehyde, considered as already health threatening. And hydrogen, in Hong Kong, we cook with tongue gas, right? So 55% or close to 60% of the gas coming out from your stove is hydrogen. So the hydrogen leakage detection is very important. So we can detect the hydrogen down to 10 ppb level, right? So this is a very high resolution. And because we use the sensor array, which means different kind of sensors in the device, right? So we can generate a pattern. So we train the sensor array. We firstly flow in certain kind of gas, known gas. Then we measure the sensor response. And because we have a sensor array, so many sensors, they have, so each individual sensor, they have slightly different kind of response to this kind of known gas, right? So after looking at so many sensors, we can extract a response pattern. So for the sensor array. So after this training, so it's a learning process. So it's also the learning process we have done when we were a kid or infant, okay? So after training, so we build a library, the data library or the pattern library, so can recognize, can remember, so what kind of gas corresponding to what kind of response pattern. The next time this gas come in, so we just need to look for the pattern inside the library. We know which kind of gas it is. So that's the basic idea. So the detail we can use, for example, principal component analysis, or even more sophisticated, the artificial intelligence or machine learning, depend on how many sensors we're using. All right. So later on, we build a sensor network using 4 sensors. I want to skip a lot of detail because time really running short for me. So we build a sensor network consists of 4 sensors in the 4 rooms in my students dormitory. So living room, bedroom, kitchen, and bathroom. So each room has 1. So this is a sensor box powered with a solar panel. So by the way, these sensors are low power sensors operating at room temperature. So so all 4 sensors connect with a cell phone app. Maybe I just go fast. So this is the really sensor on top of the stove, and my student was releasing a little bit hydrogen over here, 5% hydrogen, and then some response will be caught by the sensor. And all the other sensors in our other rooms, they won't have response, okay? So I just give you an idea. So the other experiment I did was put 4 sensors in the kitchen or in 1 room and try to detect or pinpoint the location of the leakage source. Because the gas diffusion takes time from the distance between the gas leakage source and the sensor is different for different sensors. So if I skip the details, and now the gas leakage happen over here close to node 1, and node 1 will get the higher concentration than node 2 over here, then node 4, then node 3. Then you can eventually triangulate the location of the leakage source. All right, so that's the demonstration. Okay, so recently we were thinking, you know, how we can build a smarter sensor. So we tried a different kind of methods. So one of the idea came out with by a student is using a single sensor to run the classification. We call that trade the time to the space and the power consumption because we just need a 1 sensor. Here we use a temperature modulation method to introduce the dynamic behavior of the sensors. Because what happened really at the sensor surface is the gas molecular absorption desorption. But for different kind of molecule, the absorption desorption energies are different, and activation energy, the reaction with the surface oxygen is also different. So if we quickly heat up the sensor and cool down the sensor, that will generate some the perturbation on the surface. And by looking at the transient response, so for different kind of gas, the transient response different. The slope, the change, the relative change or absolute change are all different. So by extracting these features, so we see we can get the signature of the different kind of gases. So basically it's in figure F. The Y is the conductance, the X is the slope. For different kind of gases, you can already see the difference, right? So this is using one single sensor to do the job. All right, so meanwhile, we're also working on the wearable sensor. So this has 16 sensors, also sensor array, and we have AI assisted that we can tell what kind of gas it is. So this work is still under review right now. So here we use the material called the metal oxide quantum dots. So these quantum dots, we tune the composition. You can already see different composition, right? Then we generate the variation among the different sensors. And you can see the sensor response, right? So different kind of sensor material has a different kind of selectivity to different molecules. So with AI, we can tell what kind of gas we are exposed to. So this can be a very useful wearable device for the employee working in the special industry, such as in mining or some other industries, to alert the user whether there's a leakage of the carbon monoxide or methane, etc., dangerous gases. All right, I guess I'm on time. So I just talk about the nanostructure optoelectronic sensor in the beginning. Then the second half is the nanostructure chemical sensor. So both cases we use the nanostructures to build the devices, but based on the different reasons. All right. I'd like to stop right here, and thank you very much for your time.
Professor Fan, thank you very much for your talk. It's very interesting. And you put forward the concept of bionic eyes and talked about the possibility of that being a wearable device. So how do you envision it will interface with our human body? In your example, you said that their application was through the cell phone screen, but that's still through the actual eye. So how do you envision to do that?
Right. That's a very interesting question. All right, so we thought about some hardcore way to do that. That requires the brain-machine interface. You know, that's really helping. We're trying to really working on something helping the blind people to see the light again. Then we have to use this brain-machine interface. Embed the artificial retina in our existing eye, but with damaged photoreceptors, generate electrical signal through the existing nerve to deliver to our visual cortex. So that's really something we're working on, but it's not a wearable per se. It's not a wearable, but a wearable version, I would think it's possible. It doesn't necessarily need to be a vision. Eventually it would not be a vision signal. For example, you put a camera there or the artificial eye attached to your skin, right? Can generate a temperature pulse, a little bit of vibration, and tell you something that is approaching. I think that's completely possible. Yeah, but through another type of sense, give you the signal.
Well, actually, I have a question, Zhiyong. It's a very nice talk.
Thank you.
And I noticed that you have this wearable device on the
UV sensor, right?
Not this for gas sensor.
Oh, the gas sensor, yeah.
So what is the purpose of that sensor?
Well, that's in general, let's say if we hiking or we are just doing sport or running on the road, right? One simple thing we can measure is whether there's too high nitrogen dioxide, sulfur oxide concentration on the road, right? If that's the case, you should not run over there. Right? So that's a very simple health-related application. But also for the workers in the special industry, like the mining industry, right? You need to go deep in the well and, you know, right? So then there could be a leakage of some kind of dangerous gas, give you immediate alarm, then you can just run away from that dangerous situation. So these are the applications that we are thinking of, yeah.